This is Mr. Anderson for Kellogg Community College, looking at Section 7 of Chapter 9, Applications of Exponential and Logarithmic Functions. We're going to take a look today at doing some more difficult story problems, and I'm going to pick the story problems from the book, which is something you can read along, but I will be kind of putting down the important information up here on the screen. We'll take one problem at a time. For the 7 here are going to be dealing with usually solving for one of the exponents in the problem. So you're going to see a lot of the similar problem-solving processes here. So in April 2006, it was estimated that Facebook had a total of 11.755 million users, and its growth rate was 1.019 raised to the t power. So it was growing at 10.9% per month. So this is a monthly growth rate right here. And the question becomes, in part A, when will this hit 1 billion users? Now this has actually already happened, but according to this growth model, when will this happen in terms of months? What this is going to do is it's going to have you, since we're talking about millions of people here, we're going to change 1 billion to the target of 1,000 million. So when did Facebook, if this was the correct data and growth rate from April 2006, when did they hit 1,000 million, which is 1 billion? And to find that t time, we would have to plug our 1,000 in for our answer and solve for the letter t. Now to do this, what I would do is try to get everything to the one side, so I'm going to divide both sides by 11 and 755 thousandths on both sides. Now to do this, this would get my base of my exponent all by it, well, at least more alone, so this is 1.109 raised to the t, and this 1,000 divided by 11 and 755 thousandths becomes rounded to 85.07, or 85 and 7 hundredths. From here, what we're going to do is we're going to simplify. To find t, we're going to use the change of base formula. The change of base formula says the log of my answer divided by the log of my base will give me t, or that exponent. So if I divide these two, this gives me an approximation, which is 42.95 months, or about 43 months. So late 2009 would be when, because that'd be about 42 months from April 2006, would be about when Facebook got to its billionth person. Now part B of this question asks about the doubling time. Or when would Facebook double its population according to this growth rate? When we have a doubling time problem, the answer to our problem is 2. So we plug 2 into f of t, and we ignore the start, because the start has nothing to do with how fast something is growing. So you can also see that if you did this problem very straightforwardly, where you took your 11.755 and doubled it, so on the left-hand side, you'd have 2 times 11.755 is equal to 11.755 times 1.109 raised to the t power. See, if you divide both sides by your 11.755, you can see that the start really doesn't have anything to do with the idea of your doubling time. Your doubling time is just putting 2 in for your answer. So to find t, your 2, which was plugged in for your answer, is going to be log of 2 divided by log of 1.109, and this will give you approximately the doubling time for if Facebook was growing this fast. Facebook would double every 6.7 months. So roughly every 7 months, Facebook would double if it was growing at a 10.9% growth rate. In problem problem number 4 on page 634, what we're looking at is the growth of ethanol In 1980, ethanol was being created with the equation of 0.18 billion gallons with a growth rate of 13.7%. So ethanol is being created. This is the start of the ethanol in billions. The growth rate is 13.7% because it's the percentage is always going to be the one that's above or below 1 in the straightforward annual or monthly or incrementally increased equations here. So in 1980, this is the equation, and in part A, the question is, when will we get to 5 billion? So what we're going to do is put 5 in for my answer here, and then type 0.18 and 1.137 raised to the t power. Divide both sides by 8.18, and what we get here is 27.78 is equal to 1.137 to the t power. Then we use our change of base formula to find t, where we put our answer, 27.78 divided by 1.137. And those, we've got to take the log of these. Whoa, really got ahead of myself. You don't just divide these two numbers, you take the log of your answer divided by the log of your base, and this will give you the exponent t. So you get the answer of 25.89, roughly 26 years. So the answer to this problem would be in 2006, or a little bit before 2006. Part B is just asking about the 25 billion mark. And we would do the same process as we did over here, but instead of 5, we're going to use 25. 0.18, 1.137 raised to the t power. Divide both sides by 0.18, so that gives us 138.89 is equal to 1.137 to the t power. Then we use our change of base formula to find t. This time I won't forget the log here. The log of 138.89 divided by the log of 1.137. And that's going to give us an answer of approximately 38.43. So if this growth rate continues for the 38 years, we will be making 25 billion gallons of ethanol fuel in 2018. That would be 38 years after 1980. The next problem here talks about a rumor mill. And the rumor mill is talking about, or it's hypothesized that the rumor mill is this equation. The equation is y equals 20 times 3 to the t, where t is a number of days. So this is saying like, hey, we've got a rumor, 20 people know it, and this triples every day. So this would be like 20, and then triple that would be 60, triple that would be 180, and you just go and go and go again. So part A is asking for when would 1,000 people know? So when would 1,000 people know the rumor if it tripled every day? So starting with 20 people tripling every day, we're going to type in 1,000 for our y, 20 times 3 to the t, divide both sides by 20. This is one of my favorite problems here because we get 50 equals 3 to the t. And if you've been paying attention to the notes that I've given you, this has been in the this has been in my notes in several places where 3 to the what power is 50. So to find t, we're going to go log base 50 or log base 10 of 50 divided by log base 10 of 3, or just common log. And that was going to give us a total of approximately 3.56 days. So it'll take 3.5 days for 1,000 people to hear this rumor if it does increase by that. Now part B, it just asks about the doubling time. And again, doubling time is very straightforward. It's 2 equals 3 to the t power. And 2 equals 3 to the t power is just log base 10, or common log of 2 divided by common log of 3 is equal to about half a day. or at least 2/3 of the way through the day, because that would be zero point 0.6 repeating. So roughly 2/3 of the way through the day is about the time for this to double. Since at the end of the day it triples, so you're looking at about 2/3 of the day for it to double. All right, problem number 8 is one of our first decay problems. And in one of the earlier videos, I made a mistake that I assumed that the equation was talking about people, but that's not the case. This is the percentage of success that there's a smoking prevention program where people can call in and get counseling or help to help them stop smoking. I thought this was 21.4 people in the previous video, which sounded pretty nice, but that's really not what the problem was saying. 20.4 is the percent success rate, so this is the percentage of success. And what happens over time is that that success rate is going to go down. In fact, it's going to drop by a decay of 8.6%. Now, if you're wondering how am I getting a decay of 8.6%, but if I take my 0.914 and add to it my 8.6%, I'm going to get a total of 100%. So by subtracting this percentage from 1, I can figure out that this is actually dropping 8.6 or only retaining 91% of the success every single month. So that T, or X in this case, is month. Should have a T there. So the question for A is asking, when do we have 15% success? So we have 21.4% now, but when will we hit the 15% mark? Because this is dropping. So what we're going to do is we're just going to type in our equation here and solve for T. Move the 21.4 over by division. As you see that all of these problems seem to have the same kind of pattern. We move something over, do some division. 0.70 is equal to 0.914 to the T power. Then we use our change of base formula. Our log of 0.70 divided by our log of 0.914. And then we do the division there, and we get an approximation. It's going to take about 4 months. So about 3.97, about 4 months it will take for us to drop from 21.4% all the way down to 15%. Part B of this question asks, when will it drop all the way down to 5% success? So that means that we're going to have a 5 instead of a 15, 21.4 times 0.914 raised to the T power, and divide both sides by 21.4. So 5 divided by 21.4 is 0.23, and this is equal to 0.914 raised to the T power. So what we're going to do is use our change of base formula again. So log of 0.23 divided by our log of 0.914, and we get the problem to be equal to 16.34. So it'll take about 16.34 months to get to a 5% success rate in this program. So about a year and 4 months to drop from 21% to 5%. But at least 5% are still not smoking. That's something. All right, now our last of these straightforward problems here. This one is dealing with a population growth, but the population model that they're giving us here, this P of T, this population model is giving to us in a non-continuous growth. So we have 4 and 553 thousandths billion people. So we've got 4.553 billion people in 2000 in the world. And the growth rate is going to be 1.4%. So a growth rate of 4% means that this equation, if I write the whole thing now, is going to be 4.553 billion people times 1.014 raised to the T power. So what we're going to do is try to figure out in part A here, when will we hit 10 billion? Will it happen in our lifetime? Will it happen, 100 years from now? So if our growth rate is 1.4%, when will 4.553 billion people hit 10 billion? So what we're going to do is put 10 in for my answer here, 4.553, and we're going to multiply that by 1.014 to the t power. Divide both sides by 4.553. Again, this is the same pattern that we've been doing for all the previous problems here. So we get 2.2 equals 1.014 raised to the t power. Using my change of base formula, we can figure that out, find out what year this is going to happen by going our log or common log of 2.2. Wow, I really screwed that up here. Okay, let me erase that here. Our t is equal to the common log of 2.2 divided by the common log of 1.014 gives us an answer of approximately 56.71. So at 2056 we will be at 10 billion. So it will happen probably within your lifetime. So let's go to part B right here, which talks about the doubling time. So if we are growing as a world at 1.4% per year, what's our doubling time? And remember, in doubling time problems, you don't really care about the start or the initial amount. You just care about the growth rate, the exponent, and the 2. Well, we're going to use our change of base formula here. So to find our time for the doubling, this is log of 2, and this is log of 1.014, and so what we have is about 49.86. So a 1.4% growth rate doubles every half millennium. So every half century is wow. Every half century is going to double our population. All right, so what we're going to do is move away from all of these kind of simple interest problems and simple growth problems, and what we're going to deal with is kind of a more complex, continuous interest problem. Like, let's say we have a bank account that has a continuous, not annual, continuous interest, and the continuous interest is at 3.1%. So the formula that we're going to write for our part A right here is A is equal to our P sub 0, this is our initial investment or our principal, times E to the R. Now the R, the rate has to be written like this, so it's 0.031. We don't have a percent key on the calculator, so we're going to move the decimal 2 spaces to the left, times T. So whatever we invest is going to get multiplied by E raised to the 0.031 to the T, since this is 3.1% written as 31 thousandths. So part B asks us to check, well, what happens when we have the first or the second year? Like what happens and how much are we going to get? So from the book, we're investing the $1,000 times E raised to the 0.031 times 1. And if we type that in, we'll get an answer. And the same thing goes here. Obviously, you could put this into your graphing calculator in a y sub 1 equals, like in the graphing section, and then put a little x here, and it would get both of these on your table. But typing these in, just doing 2 of them, is pretty quick too. So this is going to be $1,031.49, because we are rounding to the nearest penny, and this is $1,063.96. Again, rounding to the nearest penny. Now part C of this is going to be asking about the doubling time. So as before, we take our 2, which is our doubling point, we forget about our actual investment value, and just write E to the 0.031 to the T, or 0.031T. Because we don't really, the doubling time is based on the doubling time is based on the amount of your growth rate, and it's not really based on how much you've invested. So there's nothing in front of E to get rid of or to try to simplify, but we do have the doubling time right here. So what we're going to do is to get rid of E, or not to get rid of it, but to get the E to simplify to 1, we're going to take the natural log of both sides. If we take the natural log of both sides, our natural log of 2 is 0.69, and our natural log of e raised to the 31 thousandths t is just going to be 1 times 31 thousandths t. And we showed in a previous, we have displayed in a previous section that we can actually get the e to simplify with its inverse operation, the natural log. Now we can actually solve for t. Divide both sides by 0.031, or 31 thousandths, and t is equal to, wow, this is not going to be great for us here. If you have a 3% savings account, which is better than what my bank is giving, then it's going to take you 22.26 years to double your money. Now, for our last problem here, I am not going to do this exactly like the way the book has it written, because what none of these problems have done yet is none of these problems have actually solved for the growth rate. So I'm going to modify this problem a little bit and say, if I have the equation P, if this is for population instead of the amount of money in the bank, P in the initial population start is multiplied by e to the r to the t, e to the rt, sorry. We can use this to solve and to find a percentage of growth rate because we have this data in 2008 where there were maybe 6.7 billion people in the world, and we're projecting that in 2014 there will be 7.2 billion people in the world, and perhaps they got this information from individual countries and then extrapolated that. So the question becomes, what is the growth rate? And again, this is different than what's in the book, but I want to kind of use it because it's fair game on any test that we could not only search for t, but we can search for r. So what we have to do is use this equation and the numbers in it. So our p is going to be what we ended up with, which is 7.2. Our initial p, or our starting population, is going to be 6.7. E, the rate, is what we're trying to find, and t is the time in the number of years. Now, a common mistake is people will put 2008 or 2014 into this parenthesis, but if you put either of those in there, you're telling me it's going to take you 2,000 plus years to get from here to here, where it's really only going to take you 6, because that's the difference between the two. So it took you 6 years to go from here to here, at least 6.7 billion to 7.2 billion. Well, I'm going to rewrite this problem up here just because I don't like I don't like the look of R6, so I'm just going to rewrite it 7.2 is equal to 6.7 e to the 6r. Now we're going to divide both sides by 6.7. You see how we've been doing this all throughout the section here? And that's going to give us, let's round to 3 decimals here. Let's give us 1.075. And that's equal to e raised to the 6r. If we want to get e to simplify, we take the natural log of both sides like we did in the previous problem. Notice how that's up there. And the natural log of 1.075, or 1 and 75 thousandths, is going to be 72 thousandths. And this is going to be the natural log of e raised to the 6r is just going to be 1 times 6r. And that then lets us solve for r. Divide both sides by 6. So r will then be equal to 0.012, or 12 thousandths. But since the question is what is the growth rate, we really should put this back into a percentage. So the growth rate of this problem, or GR if you want to abbreviate it, growth rate in this problem is going to be 1.2%. So that's moving the decimal 2 spaces to the right. Well, thank you for watching the video. If you have a question, just let me know.